Hi everybody, and welcome to our acid-base notes part 4. This will be our final notes for this unit. And these notes are on what are known as neutralization reactions. A neutralization reaction is one in which an acid and a base react, and your products are always going to be water and a salt. Now, when we say a salt, what we mean is an ionic compound. All right. So for example, we could have hydrochloric acid plus sodium hydroxide. All right, and as far as figuring out what exactly the salt is going to be, this is just a double replacement reaction. All right, so we're just going to switch partners. So the sodium is going to go with the chloride. All right, and that's +1 -1, so that works. And then you're left with H and OH, which is water. But we often will write, because it helps us balance a little bit, it as HOH, or of course that is H2O. All right. So that is your classic example of a neutralization reaction. Acid plus a base giving you a salt and water. All right, so let's see some of these in action. All right, so practice problem number 1. A 25 milliliter solution of sulfuric acid, so there's my acid, is completely neutralized by 18 milliliters of a 1 molar sodium hydroxide. What is the concentration of the sulfuric acid? Well, as with any type of stoichiometry problem, and neutralization problems are stoichiometry problems, we are going to start out with the balanced equation. All right, so I have sulfuric acid, H2SO4, is going to react with sodium hydroxide, NaOH. All right, double replacement. So the sodium is going to go with the sulfate, but remember, sodium's +1, sulfate's -2, so Na2SO4. Plus my water, and again, I write it as HOH just because it helps me a little bit when it comes to balancing. Okay, so I notice right away I have some things I have to deal with. Sodium, I have 2 on the right, so I need a 2 here. All right, I now have 2 hydroxides. I only have 1 over here. I'm going to put a 2 here. Now I have 2 hydrogens to match my 2 hydrogens. So now I am all balanced. Okay, all right, once you have that balanced equation, you are going to start your calculation with the amount of the known concentration. So let's look back at the information that I gave you. All right, because at this point I'm giving you a bunch of different numbers, and it's really important that you start out with the correct number. So start with an amount. Remember, an amount in our case is going to be either milliliters or grams. It's an actual amount that you could measure out. Don't start with your concentration. Okay, so start with the amount of your known. And by known, I mean the one that you know the concentration of. Well, the question is, what's the concentration of sulfuric acid? So I'm not going to start with anything about sulfuric acid. I'm going to leave that. I'm instead going to start with my 18 milliliters of my 1 molar sodium hydroxide. That is the amount of my known. All right. So I'm going to start with that. Now it's in 18 mils and I'm using molarity. Hopefully this is kind of bringing this back to you. I'm going to immediately change those milliliters to liters. So 0.018 liters, because molarity is in terms of liters. Okay. And I'm going to change these, all right, using the molarity to moles, because I know for every 1 mole of NaOH, there's 1 liter. Remember, that's what that capital M stands for, moles over liters, okay? We're gonna now use factor label to get to moles of what we're looking for, which remember, we're looking for moles of H2SO4. So I'm gonna look at my balanced equation. There's 2 for my moles of NaOH, and they go on the bottom because I wanna get rid of them. 1 mole for my sulfuric acid, okay? I'm going to punch that into my calculator, and I'm going to get 0.0090 moles of H2SO4. Okay, great. Well, that's great. That's not the answer, because remember, I was asked for the concentration. So you need this in terms of molarity. Well, molarity is moles over liters. So you have your moles, 0.0090 moles of H2SO4. I am now going to divide those moles by the volume of your sulfuric acid. And if you look back in your problem, that was 25 milliliters, which is 0.025 liters. All right, and when I divide that out, I get 0.36 moles over liters, which is 0.36 capital M. And that is my answer. All right. Okay. So now, if you noticed in that last question, it said that it was completely neutralized. Now, how do we know that these are neutralized? Well, we go through a process that's called titration, and you will eventually do a titration lab to show you how to do this. All right, it's a process used to find the concentration of an unknown acid or base using a neutralization reaction. And I just want to briefly go over the steps with you, and then we'll go over them again when we're doing the lab. All right. A measured volume of an acid is added to a flask. So the acid is what we're trying to find the concentration of. You use several drops of what's called an indicator. And an indicator is a substance that changes color based on the pH. The indicator we're going to use in our lab is called phenolphthalein. Don't worry, you'll never have to spell it. But it's an indicator that when it's in an acid, it's clear, and when it turns basic, it turns bright pink. There's lots of different indicators out there. Bromothymol blue is another example. There's something called universal indicator. There's lots of indicators that you could use. Then you are going to use a base of a known concentration, and you slowly add that to the acid, all right, until you just get the slightest color change telling you that it has been neutralized. So some terms that might come up as you're doing these problems. Standard solution, that's the solution of known concentration. You need to know the concentration of at least one of them. Endpoint, that's the point at which the indicator color changes. That's the point where you are finished your neutralization. All right, let's take a look at your next practice problem. Okay. A 35 milliliter solution of magnesium hydroxide is neutralized with 0.95 molar nitric acid. Initially, the burette reading was 5 milliliters. At the end point, the burette read 49 milliliters. What is the concentration of the base? All right, so first thing we're going to do always is write that balanced equation. So if you'd like to pause the video now and write that balanced equation, please do so. All right, here we go. So I have nitric acid, all right, is reacting with magnesium hydroxide. Double replacement, remember, so that's going to be magnesium nitrate plus water. All right, we need to balance that out. I need 2 hydroxides there to balance that. Now I'm going to need a 2 here, and now I'm all balanced. All right, so remember, we always want to start with the amount of our known. So let's figure out what our known is. Well, there's only one concentration given here, and that's of nitric acid. So that's what we want to start with, the amount of that. Well, what is this thing called a burette? Well, a burette is a piece of equipment that's used in titrations, and it's something that can just give you a really nice exact volume. For burette readings, I give you the initial reading and I give you the final reading. All you do for this is simply subtract. So 42 minus 5, that means I used 37 milliliters. It's as simple as that. You just take those two numbers and subtract them. So 37 milliliters of your HNO3 was used. All right, so that's what we're going to start with. 0.037 liters of nitric acid. All right, remember we're going to use, now it's back to the same situation that we had in our first example problem. We're going to use that molarity to change to moles, 0.95 moles of nitric acid per 1 liter. I'm now going to go to my base, okay? I have 2 moles of HNO3, so they go on the bottom to divide out, for every 1 mole of magnesium hydroxide. I'm going to stop there, and I get 0.018 moles of magnesium hydroxide. I'm now going to take those moles, 0.018 moles, and I'm going to divide it by the volume of my magnesium hydroxide. So it's really important that you're keeping track of which numbers go with which. So that's 0.035 liters. You divide those out. You get a molarity of about, all right, 0.51-ish molar. Okay, and there's your answer. All All right. So again, the only real change to this problem was we were using a burette where I give you an initial reading and a final reading. All you do is subtract, all right, those 45 from 42 to figure out how much was used from that burette. Okay. All right, let's take a look at our last problem to see how neutralization problems can be used in a slightly different way. Okay. All right. So what volume of 2.5 molar phosphoric acid can be neutralized by 250 mils of a 3 molar magnesium hydroxide? Again, any neutralization reaction is a stoichiometry problem, so you always want to start out with that balanced equation. So go ahead and pause the video and do that now. All right, here we go. So phosphoric acid, H3PO4. All right, can be neutralized magnesium hydroxide, MgOH2. All right, that's going to give us our double replacement. So we're going to go magnesium is going to go with the phosphate. Magnesium is +2, phosphate's -3. So it's Mg3PO4 2 plus our waters. Okay, we have to balance this out. I see I have 3 magnesiums here, so I'm going to go ahead and put a 3 here. I have 2 phosphates. I'm going to go ahead and put a 2 there. I now have 6 hydrogens. I'm going to go ahead and put the 6 in front of water. I have 6 hydroxides. This works out great. All right, so what volume of phosphoric acid? So you're going to end with a volume, and we know we're dealing with molarity, so it's going to end in liters of H3PO4. All right, great. Remember, you're always starting with an amount, okay? And actually in this problem, there's only one amount. What volume of 2.5 molar phosphoric acid can be neutralized by 250 mils? So here we go. We're going to start with 0.25 liters of magnesium hydroxide, and we want to get to liters of phosphoric acid. We're going to be able to use molarity and the balanced equation to do that. So I'm going to change from my liters to moles using my molarity of magnesium hydroxide. So right there, that means I have 3.0 moles of magnesium hydroxide for every 1 liter. Okay. I'm going to use my mole to mole ratio to get to phosphoric acid. All right, I want to get rid of magnesium hydroxide, so they're going in the bottom. I want to go to moles of phosphoric acid. So it's a 2 in front of the phosphoric acid. It's a 3 in front of the magnesium hydroxide. Okay, great. Now, final step, and this is a little different than our past problems. Final step is I'm going to use the molarity of phosphoric acid to go from moles to liters. Remember, molarity can be flipped upside down. So 2.5 capital M, I can put the 2.5 moles in the denominator and 1 liter in the numerator. I'm going to check to make sure things divide out. Liters of magnesium hydroxide, liters. Moles, moles. Moles of phosphoric, moles of phosphoric. I'm left with liters. That's what I need. When you end up punching all of this in, you get about 0.20 liters of phosphoric acid. All right, we're definitely going to do some more practice with this. I hope everybody has enjoyed our unit on acids and bases. Take care.